Section 10.2, we're going to talk about correlation, and in section 10.3, we're going to talk about something called regression. We say that correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. So one way we look at correlation, or look to see if there is a correlation, is by plotting something out. So if we take each person and plot out how many hours they studied and plot that compared to what their grade was. So for example, this person looks like maybe they studied a little less than 5 hours and they got maybe a 65% on their test. Whereas somebody over here, maybe this person studied 20 hours and got about, looks like an 82 or 83% on their test. So we can see that there's some sort of correlation. In other words, the more somebody studies, the better they usually do on the test. So this would be data that is correlated. That is, the hours of study versus the grade. There is some correlation between those two variables. Or another example, suppose we're talking about musical singles that are sold and the number of weeks it's been in the top 40 on the charts. This graph shows that the longer a single has been in the top 40, the fewer are sold. So if something has been in the top 40 for 10 weeks, you're not selling as much anymore. But if you've only been in the top 40 for 1 week, then you're selling a lot. So there is some correlation between those two variables, the number of singles that you're selling versus the number of weeks you've been in the top 40. You want to be very careful about what we're talking about. Notice we are not talking about causation, we're talking about correlation. And as the common phrase goes, correlation does not imply causality, or correlation does not imply causation. Meaning that just because two variables are correlated does not mean that one causes the other. So if you look at my graph here, I plot out the number of Facebook users on this black line, and you can see back in 2005 it was only 5.5 million, but began to grow, and by 2011 there were 750 million users. Well, on the same timeline, the Greek debt crisis began to explode. So in 2005, they were $3.6 trillion in debt. And by 2011, they were $16.82 trillion in debt. Or rather, I guess we're looking at the yield on the 10-year Greek government bond, which corresponds to the debt crisis in Greece. So you can see that these two look like they're correlated. As one goes up, the other goes up. However, there's no reason to think that the number of Facebook users caused the Greek debt crisis to spiral out of control, or vice versa. There's no reason to think that the Greek debt somehow causes Facebook to get more users. So you want to be careful about how you interpret the results. We are never saying necessarily that one variable causes another. All we are saying is that there is some correlation between the two. The cause of one or both of the variables may be something else. So the definition of the linear correlation coefficient is the measure of strength of the linear correlation between the two data values, between the paired quantitative x value and y value in a sample. Let's take a look at some scatter plots of data and look at the correlation coefficient between the two. So suppose we had an x and a y axis here for an x variable and a y variable. This data in this graph looks like there's no correlation between the two. We could be higher on the x-axis, but that doesn't tell us or suggest anything about where we are on the y-axis. So if you look at, and we'd say that the correlation coefficient is r close to 0. In this case, maybe there's a little bit of correlation. It looks like for the further we go out on the x-axis, maybe the further down we are on the y-axis, but that's not necessarily the case, and so it doesn't have a strong correlation, but there might be some correlation there. So as the correlation goes up, in other words, as these kind of cluster together, you see that the correlation coefficient goes up or down in the negative direction, but it gets further away from zero is the big idea. So these guys, the last two examples, here my correlation coefficient R equals 0.9, these look pretty well correlated. So as I go up on the x-axis, my value on the y-axis also goes up, which gets me closer to that straight line that's going in the diagonal up direction. I could also be going down in the diagonal direction, which means as I go further in the x direction, I'm going down in the y direction, so I have this negative correlation. So when you're going down, you're going to have a negative correlation coefficient R, and when you're going up, you're going to have a positive correlation coefficient R. So notice in this one, again, we're kind of going downward, but it's not as strongly correlated to this as this one. So it's going to be a negative value, but it's not going to be as far away from zero as 0.99 was. We're only at 0.7, but in the negative direction. So consider this example. The paired values of the consumer price index and the cost of a slice of pizza is below. Is there a linear correlation between the CPI and the cost of a slice of pizza? So we won't actually calculate this yet, but we'll see some examples in a moment where we do. But just to get an idea of what's going on, we want to calculate that linear correlation coefficient, that R value. In order to do that, we need the formula to calculate R. That is this formula here. So everything here should look familiar or should be recognizable. N is going to be the sample size, in this case 6. The sum of x times y, that is for each x and y, we'll pick one row to be x and one row to be y. You multiply them together and then do that for each of these sample pairs and then add them all up, and then minus the sum of all the x values times the sum of all the y values. And then same thing in the denominator. Of course, now we're squaring all the x's and adding them, and then minusing the x's added together and then squared, all under a square root. So you can tell this formula is very complicated, so we're actually going to use Excel to do our calculations for us. R is the linear correlation coefficient for a sample. We say that rho is the linear correlation coefficient for a population. So this P looking letter is the Greek letter rho. So in general, we're going to take the null hypothesis to be that rho equals 0. In other words, there is no linear correlation. H1 is going to be that rho does not equal 0. So there is some linear correlation. If our linear correlation coefficient, after we calculate it using Excel, is greater than a critical value that we're going to look up in the table of critical values for the correlation coefficient, then we're going to reject the null hypothesis. In other words, then we would reject the idea that there's no linear correlation and say that there seems to be some linear correlation. So find this table, the table of critical values for correlation coefficient in Canvas. So let's look at a hypothesis test using the critical value method. And there is a p-value method for correlation, but we're going to focus on the critical value method in this section. Use the paired pizza price and subway fare data in the table below and a 0.05 significance level to test the claim that there is a linear correlation between the costs of a slice of pizza and the subway fares. So we're going to follow the same steps, even though this may be a little simplified compared to what we were talking about in previous sections. But step one, we're going to identify the claim, and our claim is that there is some linear correlation. which means we're claiming that rho does not equal 0. There is some linear correlation. The opposite then, in this case, is that there is no linear correlation, which means rho is going to be 0. Then, as we mentioned earlier, the null hypothesis is that there is no linear correlation, so rho equals 0. And the alternative hypothesis is that rho does not equal 0, so that, in other words, there is some linear correlation. Of course, we're working with a 0.05 significance level. Step 5, we're going to calculate the correlation coefficient R, but of course, like I mentioned, we want to use Excel for this. So I get that R is 0.988. So now we got to look up the correlation critical value for n equals 6. Since there are 2 samples involved in calculating R, we're going to use a n-2 degrees of freedom for these problems. So when we're talking about correlation, the degrees of freedom we're using is n-2. So in this case, my sample size is 6, so my degrees of freedom will be 4. So you're looking at the critical values for the correlation coefficient, and of course I'm shortening the name, but it's the critical values for the correlation coefficient. And since, like we said, our sample size was 6, so our degrees of freedom is 4, and we're using a 0.05 significance level, so that our critical value is 0.811. So we found our critical value to be 0.811. Now, we compare the absolute value of our correlation coefficient, R equals 0.988, with that critical value. And since the absolute value of 0.988, which is just 0.988, is greater than our critical value, we can reject the null hypothesis. So, of course, we include the absolute value just in case our correlation coefficient happened to be negative. But in either case, if the absolute value is greater than the critical value, we're rejecting the null hypothesis. So the claim was that there existed some correlation between subway fares and pizza costs. We rejected the null hypothesis that there was no correlation, so there does appear to be some correlation. Let's try this example. Listed below are systolic blood pressure measurements obtained from the same woman. So, in other words, we have 5 different women, and we obtained this, from the same woman the right arm blood pressure measurements and the left arm blood pressure measurements. Is there sufficient evidence to conclude that there is no linear correlation between right and left arm systolic blood pressure measurements? We'll use a 0.01 significance level. So the claim is that there is no linear correlation, so rho equals 0. And the opposite, of course, is that rho does not equal 0. So again, we'll get our null hypothesis as rho equals 0, and our alternative hypothesis, rho does not equal 0. Our significance level in this case is 0.01. So using Excel, of course, I'm going to calculate the correlation coefficient. And I keep telling you to use Excel. What you'll want to do is take a look at the video after this one that will explain how to use Excel to calculate this correlation coefficient. Step 6, we're going to look at the critical value for our correlation coefficient, and in this case, our sample size was 5 women, so our degrees of freedom is 3. We're using a 0.01 significance level, so my critical value is 0.959. We found our critical value to be 0.959, so we take our correlation coefficient, its absolute value, and compare that to the critical value. In this case, it's less than our critical value, so we're going to fail to reject the null hypothesis. And since we didn't reject the null hypothesis, which was the same as our claim, we cannot reject the claim that there is no correlation between blood pressure in both arms. In other words, it's possible there is no correlation between blood pressure in both the arms.